Hello everyone, welcome to the next session on algorithmic problem solving. In this session, we consider the interval partitioning problem. The input to the problem is a set of intervals, each with its start and finish time. The goal is to partition the set of intervals into subsets of mutually compatible intervals such that the number of such partitions is minimized. Here we consider an example. The input to the problem is a set of 4 meetings. The red meeting runs from 0800 hours to 1300 hours. The blue meeting runs from 0900 hours to 1100 hours. The green meeting runs from 1400 hours to 1500 hours and the green one from 12 noon to 1600 hours. The goal is to schedule these in fewest number of meeting rooms. The optimal solution is of size 2. Greedy heuristics. Greedy algorithms use special criteria or heuristics based on which choices are made in the algorithm. The greedy choice makes the algorithm efficient. Here is a template we shall use for a greedy algorithm. We sort the intervals according to some criterion. Then we loop through the set of intervals in that order. We try assign the next interval to an existing free resource. If none of the resources are free, we allocate a new resource. First, we consider the heuristic earliest start time. In this case, we schedule jobs in order of earliest start time. This gives us the optimal solution. In the example shown, first the red interval is allocated. Next the blue interval is taken into consideration. Since the red and the blue intervals intersect, the blue interval is allocated a room different from the red one. Then, the yellow interval is considered. Since the start time of the yellow interval is greater than the finish time of the blue one, the yellow interval is scheduled in the same room as the blue. Finally, the green interval is considered. Since the start time of the green interval is greater than the finish time of the red one, the green interval is scheduled in the same room as the red. This leads to an optimal solution with 2 rooms. In this case, we schedule jobs in order of earliest finish time. In the example shown, first the blue interval is assigned a room. Next the red interval is considered and assigned room different from that of the blue interval. Then the green interval is considered and is assigned the first room, since the blue interval has a finish time earlier than the start time of the green interval. Finally, the yellow interval is scheduled. Since it intersects the red and green intervals, it needs a third room. This does not give us the optimal solution of 2 rooms. In this case, we schedule intervals in order of latest start time. In the example shown, first the green interval is assigned a room. Next the yellow interval is considered and assigned room different from that of the green interval. Then the blue interval is considered and is assigned the first room, since the blue interval has a finish time earlier than the start time of the green interval. Finally, the red interval is scheduled. Since it intersects the blue and yellow intervals, it needs a third room. This does not give us the optimal solution of 2 rooms. Next, we consider the latest finish time heuristic. In this case, we schedule intervals in order of latest finish time. First, we schedule the yellow interval. Next, the green interval is scheduled and since it intersects the yellow, it goes to a different room. Next, the red interval is scheduled. Since the finish time of the red interval is earlier than the start time of the green interval, the red interval is scheduled in the same room as the green. Finally, the blue interval is scheduled. Since the finish time of the blue interval is earlier than the start time of the yellow interval, the blue interval is scheduled in the same room as the yellow. This gives us the optimal solution. In this case, we schedule intervals in order of their length or duration. In the example shown, first the green interval is scheduled. Next the blue interval is scheduled. Since the blue interval has a finish time earlier than the start time of the green interval, it can go to the same room. Then the yellow interval is scheduled. Since it intersects the green, it goes to a second room. Finally, the red interval is scheduled and since it intersects the blue and the yellow intervals, a third room is allocated for it. This does not give us the optimal solution. To implement the algorithm, we need a priority queue. This is required for selecting the next resource. Let us assume we employ the earliest start time heuristic to select the next interval with start time s for scheduling. To select one of the existing resources, an earlier scheduled task on the resource must have finished at a finish time f less than equals s. Among options, we select the one with the minimum f. To implement the priority queue, we will use a min heap. A heap operation which is required is the heapify. If the 2 subtrees of a node V are heaps, heapify converts the entire subtree rooted at V to a heap in order log n time. Another heap operation we will use is to update the value stored at the root. If the root value of a min heap is reduced, no further changes are required. If the root value increases, we need to apply a heapify. Thus the update root operation also takes order log n time. Another heap operation we will need is the insert. To insert a key value to a heap, we add it to the end. This is a leaf node v. Then starting at v, we follow the leaf to root path, exchanging a key value with a parent node whenever the heap condition is violated. The insert operation takes time proportional to the height of the heap, which is order log n.
An example of a mean heap is shown here. Note that the key value at any node is less than or equal to the key value in the child nodes. Suppose we need to add a key value 1 to our mean heap. First, we add the new key right at the end of the heap. We compare with the key value of the parent. Since 1 is less than 19, the heap property is violated, and the key values must be exchanged. Since 1 is less than 2, the heap property is violated, and the key values must be exchanged. Now the heap property is satisfied. This completes the heap insert operation. Now, consider an example where the key value at the root of the mean heap needs to be updated. If the new key value is less than the existing value, the heap property is not violated by the change. However, in this example, the new value 38 is greater than the existing value 2. We need to verify if replacing 2 with 38 violates the heap property. The left and right subtrees of the root were heaps prior to the change. The change only affected the root. Hence, the left and right subtrees of the root are heaps after the change as well. We need to check if the key value at the root violates the heap property. The minimum of 17, 38, and 19 is 17. So we need to exchange 17 and 38. Since 35 is the minimum of 35, 38, and 51, we need to exchange 35 and 38. This is the final state of the heap after heapify has completed. Here we have a simple outline of a left-to-right sweep algorithm based on the earliest start time first heuristic. We first sort the intervals based on their start times. If the kth interval can be scheduled with any conflict with any other class in any of the classrooms, we schedule it in the same. Else, we allocate a new classroom and schedule the kth class there. This heuristic yields the optimal solution, allowing us to schedule using the minimum number of classrooms. Consider the kth class to be scheduled with start time s, k, and finish time f, k. Consider the last class allocated to each classroom. Some of these classes are still running at time s, k, and these classrooms are not available. If the last class allocated to a classroom has finish time f where s, k, is greater than or equal to f, the kth class may be scheduled there. The classrooms may be stored in a mean heap with the finish times of last allocated jobs as the key. For a class s, k, f, k to be scheduled, we compare s, k with the key value f at the root of the heap. If s, k is less than f, then the start time is less than the finish times of all the classes represented in the heap. Hence none of these classrooms can be used to schedule the class with start time s, k. A new classroom must be allocated. If s, k is greater than f, the classroom with f as the finish time of the last allocated class may be reallocated to the class with start time s, k. In this case, the key value of the root is increased to f, k, and an update root operation is performed to maintain the heap property. Since all heap operation used are order log n, the algorithm runs in order n log n time. Pseudocode and Python code snippet of a simplified algorithm are shown here. We consider the classes in the non-decreasing order of their start times. We maintain free CR, a list of classrooms used earlier but free now. We also maintain busy CR, a dictionary of busy classrooms. A key value pair A B in busy CR represents a class a schedule in classroom B. We initialize number of allocated classrooms to 0. Consider the start time s of the next class in our ordering. If the last allocated class has a finish time earlier than s, we allocate the classroom to the free CR pool and remove the classroom from the busy classrooms dictionary. We also need to decrement the allocated classrooms count. To allocate the current class under consideration, we remove a classroom from the free CR list and allocate the class in the same classroom. If no classroom is free, we allocate a new classroom for the class to be scheduled. This algorithm takes time order ND, where N is the number of classes and D is the number of allocated classrooms. Here we summarize the greedy heuristics we discussed. Among the 5 heuristics we discussed, only the earliest start time first and the latest finish time first strategies yield solutions using the minimum number of classrooms. We considered 2 possible implementations of the earliest start time first heuristic. The heap-based solution takes order n log n time, and the dictionary-based solution takes order n d time. Here n is the number of classes to be scheduled, and d is the minimum number of classrooms required. Consider the start times and finish times of events to be scheduled according to the earliest start time first heuristic. For event I, the start time is s list I and the finish time is f list I. The event with start time 1 and finish time 2 is scheduled first, in classroom 1. Next, the event with start time 2 and finish time 5 is scheduled. It can reuse classroom 1 since it gets free at time 2. The next event starts at time instant 3 and ends at time instant 6. When it starts, classroom 1 is not free. So, classroom 2 is allocated. The next event has a start time 4 and finish time 5. When it starts, both classrooms 1 and 2 are occupied. So, this event is scheduled in classroom 3. The next event scheduled starts at time 7 and ends at 12. It can reuse classroom 1, which is free, at the start time 7. The next event starts at time instant 11 and ends at 13. It can use classroom 2. When it starts, classroom 1 is still occupied. And the previous event in classroom 2 has finished. The next event starts at time instant 11 and ends at 13. It can use classroom 2. When it starts, classroom 1 is still occupied. And the previous event in classroom 2 has finished. The next event has a start time of 21 and a finish time of 24. When it starts, all classrooms are free. The event is allocated to classroom 1. The last event to be scheduled has a start time of 22 and a finish time of 25. When it starts, classroom 1 is occupied. The event is allocated to classroom 2. The solution uses 3 classrooms. This is optimal since between time instants 4 and 5, 3 events overlap and must be scheduled in 3 different classrooms. Thank you. This course is brought to you by Elahay Technologies.